Welcome back to the lectures on chemistry and the course on introductory molecular spectroscopy. The theory of spectroscopy is essentially developed using quantum mechanics. The quantum principles for molecular energy levels are understood by the solution of the Schrodinger equation, and in this lecture and probably the next one, I shall give a brief summary of the elementary quantum results that we shall use for the whole course. In the previous course to this, called Chemistry 1, which is available from the NPTEL website, ac.in or nptel.ac.in. I have introduced basic principles of quantum models, that is elementary models of quantum mechanics, by about 10 to 15 hours, and therefore that may be used as a reference every now and then, but here I shall give only the summary and the results that we shall be using for vibrational and rotational and also magnetic resonance spectroscopies. Okay. So, let me start with the fundamental equation that we need to be concerned with, the Schrodinger equation. The time dependent Schrodinger equation is given by this formula, by this equation, IH bar, the partial derivative of psi with respect to time is equated to the operation of the Hamiltonian operator of the system under study acting on psi, and psi here, which I shall use as a capital psi, is a function of both the coordinates of the system and is a function of time. So, that is what is denoted as psi. However, if h is independent of time, then the equation IH bar dou psi by dou t is equal to h psi can be reduced to a simpler time independent equation. H psi is equal to E psi. This psi is different from capital psi which is used here, and the relation is the psi of R t is factored into a function which depends only on the position coordinates of the system and a function which is only time dependent. And as a result, if you substitute that into this equation, you will get the time independent Schrodinger equation H psi, which is given as the kinetic energy operator plus the potential energy operator acting on psi is equal to E psi, where this psi is the psi of R. That is the same thing as what you see here. Okay. Quantum mechanics for spectroscopy uses both time dependent and time independent Hamiltonians. The molecular energy levels in the absence of the electromagnetic field are obtained by the solution of the Schrodinger equation, which is time independent. In the presence of the radiation, the excitation of a molecule is often studied using a time dependent Hamiltonian, for which one needs to use the time dependent Schrodinger equation and use approximation procedures such as perturbation theory to arrive at results for the intensity of radiation that gets absorbed or emitted. So, spectroscopy uses both of these and in different domains, but for our problem we need to have the knowledge of the energy levels of the molecular systems, some mental picture has to be there, and therefore let me introduce the elementary mathematics and the model problem results right away in this lecture. Okay. First of all, when you say the time independent Schrodinger equation is H psi is equal to E psi, it means a whole series of wave functions E n psi n, where n can be an integer, n is an integer, n is an integer, and it can be finite or infinite. For magnetic resonance systems, the wave functions are finite. For optical resonance using harmonic oscillators, the electronic wave functions and so on, the n can be infinite. Therefore, a whole group of wave functions, these are called eigenfunctions, are used, okay, and the Ens are called eigenvalues. These are what you will obtain if you measure the energy of the molecular system. One of these is what you will get with some probability. Therefore, the wave function in general for a molecular system, an arbitrary wave function of the system, is expressed as a linear combination 1 to whatever number. Let us write infinity here for optical resonance. What we have is a linear combination coefficient and the eigenfunctions. This is called the linear superposition principle. In this model, Cn's have very specific properties associated with them, and since I mentioned that the psi n's are eigenfunctions, they can be normalized and they are also orthogonal to each other, being eigenfunctions of the Hamiltonian operator, and the Hamiltonian operator is a Hermitian operator. Hermitian operators are associated with observable properties, experimentally observable properties. So, the wave functions are normalized, the wave functions can be normalized, the wave functions are orthogonal, and they have the specific property, namely the integral psi n star psi n over all the coordinate system, a space available to the system is psi m is delta n m, which is the Kronecker delta. Delta n m is 1 if n is equal to m and is equal to 0 if n is not equal to m. With this property, you can see that the wave function phi, which is written as a linear combination of all the eigenfunctions, the coefficient Cn square or probabilities of finding the system in the state psi n with an energy E n. What it means is that if you have an identical copy of the system, many copies, and you repeat the experiment of measuring the energy of the system, the energy would be one of the possible eigenvalues, the outcome would be one of the possible eigenvalues, and the state at which the system will remain would be the eigenstate of that eigenvalue. Therefore, psi n would be one of the measurable state of the system and E n is the energy associated with it. What is the probability that when you look at the system that you get one psi n or another, that probability is given by the linear combination square Cn square, and therefore, since it is a probability statement, what it means is that all such probabilities should add to give you unity. That is, the system will be in one of the eigenstates that when it is measured. So, this is a fundamental principle, and there are simple model problems to illustrate this. So, let me just give you the 3 model problem results: the particle in a box, one model, the particle on a ring, the harmonic oscillator, which is very important for vibrational spectroscopy, and then the hydrogen atom, which is used as the basis for understanding molecular states of all the molecules, all the atoms and molecules with more than one electron. Hydrogen atom is the simplest one electron model that could be solved, and and all these models, particle in a box, on a ring, harmonic oscillator, they all have exact solutions. So, let me recall in the rest of this lecture and also the next lecture the primary results that we need to know: the eigenvalues, the model, the eigenvectors, etc. As I mentioned in the beginning, a more detailed, more elaborate process of how we get these things is there in another course, Chemistry 1, which preceded this course. Therefore, you may see the videos at your convenience on those specific topics if you need more information. Otherwise, you can also write them on the discussion board. Now, let us start with the simplest model, namely the particle in a box model. This is essentially a potential free model inside the box, and the potentials are infinity outside the box and also the wall. So, what it means is that you study the Hamiltonian, you study the solutions of the Hamiltonian H psi is equal to E psi, or H psi n is equal to E n psi n, using the Hamiltonian, which contains only the kinetic energy of the particle, which in quantum mechanics is given in one dimension by h bar square by 2m d square by dx square. H bar is obviously h by 2 pi, Planck's constant. Please remember these things all the time, Planck's constant, and therefore, you solve this equation for the potential model, namely V of x is 0 for x in a certain region, maybe the length of the box being L, and V of x is infinity otherwise, meaning x less than or equal to 0, x greater than or equal to L. Okay. So, this is the box model, and what are the solutions? The solutions are the wave function psi n of x is normalized using the box length root 2 by L sin n pi x by L, and the n can take the values 1, 2, 3, etc. all the way to infinity, and the energies E n's are given by this formula h square n square by 8 m L square. So, the model of the mass of the particle and the length of the box, which are the parameters for this particle in a box model, determine the spread of the energies and the discreteness in the energy, because h square by 8 ml square has the energy unit or energy dimension, okay, and the n square is the quantum number which tells you the energies are 1, 4, 16, 9, 16, 25, 36 times this base unit, and the base unit of energy for that model depends on the length of the box that you choose and also the mass of the particle that is being studied, or the mass of the molecule that is being studied, the mass of the electron, whatever that you do. This is the solution. This is the simple one process that you can immediately recall, and of course, you have the same relations as I mentioned earlier, namely the psi n star, which being a real function is the same as psi n of x, and psi m of x, and dx. The range for the particle is 0 to L, the motion within the box, and this is the d tau that you talked about. This is delta m n, meaning that the wave functions are normalized when n is equal to m. The probability of finding the particle inside the box is unity for all states of the system, and the second is that the wave functions are orthogonal to each other. So, this is the summary result, and therefore, any particle wave function in principle any arbitrary wave function or any arbitrary state of the system inside the box can be written as the sum n equal to 1 to infinity C n root 2 by L sin n pi x by L, and for this state the average value of the energy turns out to be sum over n equal to 1 to infinity C n square, the absolute square, times h square n square by 8 m L square. This is the average value for the energy, but the average is obtained only when you do many measurements and take the average of all of this. Otherwise, every individual measurement will give you one of the energies, and it will also fix the state into that eigenstate. So this is the particle in the box model. The next important model that you have to remember for vibrational spectroscopy is the harmonic oscillator. The harmonic oscillator Hamiltonian is the potential energy is given by the potential energy which is parabolic or which is quadratic, and the kinetic energy is of course p square by 2m, which is written as minus h bar square by 2m d square by dx square plus half k x square, and k is the harmonic force constant. Expressing the stiffness of the harmonic motion, whether the motion is very rigid or whether the motion is very flexible, the value of k will determine the harmonic, the extent to which the system can be harmonic. So k is system dependent, okay, and every harmonic oscillator has a fundamental frequency, the classical frequency of the oscillator is known from elementary physics, and that frequency nu is given by 1 by 2 pi square root of k by m. Again, you see the parameters which determine the system are m and k, and the frequency is expressed in terms of k by m, the ratio k by m, the square root. This is of course classical. What happens when you solve the Schrodinger equation for this system with h psi n of x is equal to E n psi n of x, you get again infinitely many energies, but one thing one should remember is that n can be 0, 1, 2, 3, etc. The integers n is equal to 0 is also allowed. The solutions turn out to be for E n given by this formula, namely h bar omega times n plus a half, n plus a half, and omega is 2 pi times nu, the same nu that you have here. Therefore, you see that the harmonic oscillator energy is given in terms of h nu, if you want to write that, because there is a 2 pi in the denominator that cancels this, h nu into n plus a half, and the half ensures that n equal to 0 is also an allowed value, which means even if the harmonic oscillator is in the lowest possible energy state with no quantum number input to that, it still has an energy called energy equivalent to half of the h bar omega, and h is the Planck's constant, omega is its natural angular frequency. What are the eigenfunctions for the system? The eigenfunctions are given by a combination of the Gaussian e to the minus alpha x square by 2 and the Hermite polynomials h n root alpha x. What is alpha? Alpha is square root of k m by h bar square. Again, alpha is the physical constant associated with the system. The mass of the harmonic oscillator and the force constant that the oscillator has. So, if the oscillator is very strong, its force constant is very high, then alpha is very large, square root of that, of course, Km. And if the oscillator is very heavy, so is alpha. So, the parameters of the system, the model that you study, are used to define the wave functions and the energies. The Nn is a normalization constant. And in the case of harmonic oscillator, x is taken all the way from minus infinity to plus infinity. Therefore, the wave functions, when you talk about the orthogonality, it is from minus infinity to plus infinity, psi n star of x, psi m of x dx is delta n m, which tells you that the wave functions also satisfy the same orthogonality and normalization relations for the harmonic oscillator. What is important with the harmonic oscillator is something unique, namely the energies are h bar omega n plus a half, meaning that the energies are all equidistant. So, if you write half h bar omega here for n equal to 0, and if you write for n equal to 1, it is 3 halves h bar omega, and for n equal to 2 it is 5 halves h bar omega, and so on. 3 7 halves h bar omega, and so on. So, energies are equidistant. Energy levels are equidistant. For a particle in a one dimensional box, of course, you remember it is proportional to n square, whatever is the unit that you have. Therefore, if you put n equal to 1 here, and then if you put n equal to 2, it is 4. N equal to 2, this is 4 times that fundamental unit, this is 1 times that fundamental unit. The next one would be 9 times 1 4. So, I believe the difference is 3 3 3. So, it should be somewhere here. Next one is 9 times, and the third one is 16 times, and so on. So, the energies are not separated from each other by the same distance in the case of particle in a box. In the case of harmonic oscillators, they are all separated by the same gap. The difference between any pair of successive energy levels is h bar omega, which would be needed later when we study vibrational spectroscopy of a harmonic diatomic molecule. In the harmonic oscillator model, you would see that the spectrum for a simple diatomic molecule contains only one line, and that one line corresponds to the difference between the two nearby energy levels. It is not possible for a harmonic oscillator to be excited to levels far away from the starting point. There are selection rules for that, but the quantum mechanics of the harmonic oscillator gives you all these results later when we need them for the spectroscopy of a diatomic molecule. Okay. The next important model, the real physical model in addition to harmonic oscillator, is the hydrogen atom. The hydrogen atom with a proton and an electron separated by a distance r the proton electron system has a potential energy given by minus ZE square by 4 pi epsilon naught r, where epsilon is the permittivity of the medium, and the hydrogen atom is a two body system, two particle or a two body system, and it can be separated into a center of mass coordinate, that is a system in which all the mass is concentrated on the center of mass, and also a relative particle system in which the relative particle has the mass mu, and that is given by the proton mp times the electron me by mp plus me, and you know that mp is much greater than me. Therefore, mu is the reduced mass is approximately the same as ME, because this will be MP and that cancels the MP, so it is about ME. And this is what we normally use in writing down the 1 electron Schrodinger equation for the hydrogen atom. We do not worry about the center of mass, the nucleus is too heavy, we do not consider the kinetic energy of the nucleus or kinetic energy of the whole atom system, but only the 1 electron system that we need to study. And the Hamiltonian for the 1 electron system is given by minus h bar square by 2 ME, the mass of the electron. It is a 3-dimensional system, therefore the kinetic energy contains 3 components. The derivative with respect to the 3 coordinates xe square plus dou square by dou y e square plus dou square by dou z e square, and the potential energy minus z e square by 4 pi epsilon naught r. Z is the charge on the nucleus, of course that is equal to plus 1. And so what you have is it is e square by 4 pi epsilon naught r, and these are the coordinates of the electron with respect to the center of mass, where it is approximately on the nucleus and so on. Therefore, this is the Schrodinger equation that we need to solve and obtain the solutions h psi n, which is now a function of the 3 coordinates x e, y e and z e is equal to E n times psi n of x e, y e, z e. So, these solutions, the psi n's and the E n's, in the case of hydrogen atom are slightly more complex than what you see in the particle in a 1-dimensional box or the harmonic oscillator. Now, it is almost like 30 minutes since we started this lecture. So, let me stop here, and in the second part of this lecture, which is continuing to the quantum mechanics, let me complete the exercise of writing down the energy levels and the wave functions for the hydrogen atom, and also the most important aspect of the hydrogen atom that is relevant to spectroscopy, namely the concept of angular momentum, would be introduced in the second lecture. The next lecture and this would be a quick summary and a review of the basic quantum mechanics that you need for understanding the rest of the course. Until then, thank you very much.